All right, ladies and gentlemen. Hey. Ladies and gentlemen, this class recording has started. So, yesterday, we did the first section of chapter 20, or we read the first section of chapter 20, and that dealt with electric charge. So electric charge is the basis for our entire unit on electricity. Yesterday, I gave you guys the sheet that did the alike but different, right? It's comparing and contrasting electric charge. So, what's the first thing that we talked about that makes electric charges all similar to one another? What's one thing that all electric charges have in common? You can look at your sheet from yesterday that we did in class. Ryan, go ahead. They are all subatomic particles, right? So here we have a chart that you guys have seen before, okay? I got to make a couple changes to this chart. Well, I guess a couple of additions. First, this part didn't transfer over for some reason. So we had that fraction right there, okay? But then, and you guys don't have this chart on your outline. Okay, this is just a chart we've looked at before, right? And then the other thing that I should add here is this word, all right? So, first, Ryan, so the one thing electric charges have in common is that they're all subatomic particles, right? Specifically, which two subatomic particles? Electrons and protons, right? Negative charges come from electrons, positive charges come from protons. Now, things that make them different. Obviously, one's positive, one's negative, okay? One more thing that they have in common. Yesterday, I can't remember if it was in this class or if it was in the other class, somebody said that protons are bigger than electrons. True, if we're talking about their masses, right? But when we talk about their relative charge, right, we see here their relative charges. They have the same amount of charge, but one is positive and one is negative. Right? Good there? So, on your outline, Roman numeral number 1, letter A, electric charge comes from, go in the blank. Electric charges come from, yes, electrons. Electric charges come from subatomic particles. And because electric charges come from subatomic particles, there's a couple of things that have to be true. First, we say that charge is quantized. Whether you remember it or not, quantization is a concept that we've brought up before. Does anybody remember when we discussed the idea of quantization previously? Anybody? What? No, I think you're actually right. What did you say? Chicken. You know what you said, you just don't want to say it. So Danny, go ahead. Hey, can we cut the chit-chat, please? Good. Psst. Hey, can we cut the chit-chat, please? It took you like a half a second to start talking again. Were you talking? No, you were talking. And now you're lying about it. And it's on recording, so. All right, back to this. Quantization. Yeah, go ahead. So we talked about quantization in relation to a Bohr model, right? And we said that electrons can be in this shell or this shell or this shell, but nowhere in between. Charge is like that, in that there is a definite amount of charge, and that charge is the charge of one electron. All other charges are integer multiples of that charge. Okay? For example, okay, I just drew a Bohr model on the board. Okay? What element did I draw the Bohr model for? That
Lithium.
lithium, and you know that because
That's 3 electrons.
it's got 3 electrons and it also has
3 protons.
3 protons. That's what the P positive stands for, right? Okay, so this is lithium. Right now, this atom of lithium has what charge?
Neutral.
It is neutral. It has no charge because
3 negatives.
There's 3 negatives, 3 positives.
3 negatives and 3 positives, right? If I do this, right, let's say that lithium loses that electron.
It's positively charged.
Yes,
And it's
specifically what positive charge does it have? 1 positive, right, or positive 1. Why? Because we have one more proton than we do electrons, right?
Yeah.
But if this happens,
And it's negative. One
Negative
negative.
one.
1 negative, right? Because now it has 1 more electron than proton,
Yes.
right? I can't wait till I get my. Hopefully, I'm talking about it as a certainty, as if I'll get it. I think I'm going to get it, but I don't know for sure. So, my new microphone that picks up. Yeah, we can hear everything. So, yeah, hopefully. All right. So, charges are all integer multiples of this charge. We go up by 1, 2, 3, 4, because you can't either lose half an electron or gain half an electron. It just doesn't work that way. All right. Now, this chart that we were working off of lists the charge, or I wrote in, the charge is listed as what? What does it say above the charge column? Relative charge, right?
Relative.
Relative scales do what?
They get the relative.
Compare things, right? By comparison, electrons and protons have the same amount of charge, but one's positive and one's negative, so they can cancel each other out. But this is not a measurement. There's no unit here. Okay? We measure the amount of charge in a unit that we call the coulomb. Okay? A guy named Robert Millikan in the 1930s, if I remember properly, did an experiment that we call the oil drop experiment, where he calculated or measured the charge of 1 electron. So while protons and electrons have the same relative charge, +1, -1, when we look at the actual measurement, it's in a unit called the coulomb, and this is the value of 1 electron. 1.60 times 10 to the -19th coulombs. Meaning, if we want to have 1 coulomb of charge, how many electrons are we going to need? Lots or little? Lots, right? One electron carries 10 to the -19th coulombs. Meaning, if we just want 1 coulomb worth of charge, we're going to need a lot of them, right? Does that make sense? Okay. So, on your outline, right, Roman numeral 1, letter B. Actually, I should do this. Hold on. Seeing as how I'm recording. Okay. So, electric charge comes from subatomic particles. Charge is quantized. The minimum amount of charge is the charge of what? 1 electron, okay? All other charges amounts are integer multiples of this charge, right? And then I just gave you the value for the charge of 1 electron and the charge of 1 proton, right? 1.6 times 10 to the -19th. Electrons are negative, protons are positive. That capital letter C at the end stands for a unit that we call the coulomb, and that's how we measure charge. Okay? Good there? All right. Because charges come from subatomic particles, that means that they are quantized. They have to come in integer multiples. 1 electron, 2 electrons, 3 electrons, right? But there's also something else that charge has to be, and that is conserved. We've talked about conservation before, right? What does it mean when we say that something is conserved? It's stored. Let's go maybe with somebody else. It's saved, right? If we measure it, what do we end up with? The same amount, right? Which, right, in essence is storing, right? But let's talk, if we talk about measuring it, right? It's always the same amount. Because charge comes from matter, specifically electrons and protons. As those electrons and protons move around, the total amount of charge is the same, right? Even though one atom might gain electrons and another atom might lose electrons, right? If we go back to this picture, right? Pat, we said that the way that it's drawn right now, this atom of lithium has a charge of what?
-1.
-1, because it gained an electron. But that means if charge is conserved, if this atom gained an electron, what else had to happen somewhere else?
And to gain a proton.
Something else would have to have lost an electron. So the total amount of charge is the same, right? I see where you're going with that, right? If this is -1 and it has more electrons than protons, if something has a +1 charge, it should have what?
One more proton.
Then
What? Then electron.
Then electrons, which is true. But we don't accomplish that by moving protons around, okay? Total amount of charge is the same at the beginning as it was at the end, and that means when electrons are transferred, the value of positive and negative charge created is equal. Like we said, if this atom's going to be -1, there has to be another atom somewhere that's what?
+1.
+1 to keep the total amount the same. All right? Good there? Okay. An object becomes charged when it has an imbalance of subatomic particles. An object becomes charged when it has an imbalance of subatomic particles. And we drew, or I drew, pictures that represent this just on the previous board, right? Over on the far left-hand side. Let me zoom in so you guys can see it a little better. Over on the far left-hand side, it says, is a neutral lithium atom. Here's the nucleus of the lithium atom. And in that nucleus, there are 3 protons. 1 there, 2 there, 3 there. They're the orange ones. Okay? You can see them. It's kind of blurry, but yeah. Dave, will you turn off the bottom light? And zooming around the outside, right, there's our 3 electrons. If the number of protons and electrons is equal, that's a neutral atom. Here, one of the electrons is gone. It still has the 3 orange protons, but now it only has 2 electrons. This is a positive, what we call ion, because now it has more protons than electrons. That is a positive, yeah. So what we call, that's how we'll write it sometimes. Here, let me do this. Right? So specifically, we can write it as, oh, I have to get my pen, hold on. Specifically, we can write it like that, okay? And then over here, same thing that we did before, right? That has more electrons than protons, okay? You can go to the bathroom for that. That has more electrons than protons, so it has a negative charge, okay? Good there? But the one thing that we really have to keep in mind from this slide here, and you don't have a space to write this, but it's important, okay? It's true that more electrons than protons equals a negative charge. And atoms will gain that negative charge by gaining electrons, okay?
So, like, say there's 2 more protons than electrons. Like, say it's a lithium, would be Li plus 3.
Yep. Yeah. There's always, like, say, integer multiples, right? Yeah. Got it. Got it. Yeah, always integer multiples. So it can be plus 1, it can be plus 2, it can be plus 3. And Pat, what we'll find is that figuring out how many electrons it has to lose or gain depends on the let's go with lose. Depends on how many valence electrons it has. So that valence electron is going to come back again. Okay? But when something gains a positive charge, it has more protons than electrons, but it doesn't do that by gaining protons. It does that by losing electrons. Protons don't move around, electrons do. Okay? Good there? Right, so any object that has a different number of protons than electrons will be charged, but if it gains electrons or loses electrons, that will determine whether it's negative or positive. Nothing happens with our protons. Okay? Good there? All right. How does this, when this happens, when we end up with atoms that have different numbers of protons and electrons, we find that they can cause changes in other objects. Objects that have an imbalance of protons and electrons will experience a change in their motion, right? If we have two likely charged objects, two negatives or two positives, they will repel each other, right?
Magnet.
Like very much like a magnet. And we'll see that when we get to the magnetism, that is related to this as well. But when they are oppositely charged, one positive and one negative, they will attract each other. And I think you saw examples of both of those in your in the discovery lab that we did on Tuesday, right? The water stream usually moved away from the rod that you place near it, okay? But like the paper discs definitely moved towards the rod, right? They'd stick to it, okay? The two little aluminum foil leaves that were in the black box, they would move away from each other, right? All because they have an imbalance of charge. Okay? Good there? All right. I'm thinking. I'm just looking at the clock. Let's just go through the rest of the next part. I was going to have you guys read something from your book, but I think we'll just go through it up here because it'll be a little bit faster to go through it. So, all right. How does this happen? Well, there are three ways that it can happen. This achieving an imbalance of protons and electrons. And we call that charging. Except I got to change something, right? Interaction between objects will result in an imbalance not of protons and neutrons, but protons and electrons. Okay, so make sure you write that down properly because you don't write, having an imbalance of protons and neutrons doesn't mean anything. Oh, sorry. We're skipping Roman numeral number 2, going down to Roman numeral number 3. All right, so on your outline, we skipped Roman numeral number 2, and we're going down to Roman numeral number 3 that says methods of charging. All right? So first, interaction between objects may result in an imbalance of protons and electrons, but that happens by transferring electrons, right? If an object gains electrons, it has a negative charge. But if an object loses electrons, loses electrons, there we go, it will have a positive charge. Okay? Nothing ever happens to protons. The protons don't move around. They're stuck in the nucleus. But the electrons are free to move in between atoms, and we'll talk way more about that when we talk about bonding. I'm missing the top of my magic pen. I don't know where it went. Interesting. I don't even remember like dropping it or anything. Like, I'll find it later, I guess. So, all right. There are three ways that this can happen. Three ways that we can get the imbalance of protons and electrons. So the first way is by friction. Okay? First, in order for there to be friction, what has to be happening? Is there friction between my hands?
Yes.
No.
No, you have to move the
There,
stick.
no,
Okay.
technically there is.
No.
No,
There
it's
is
not
not.
moving.
Friction requires movements.
Friction is
Okay.
negative.
Well, it depends. All right.
It's always making a negative force.
It always goes against the motion that we're doing. Okay. Now, here is an example, probably one that you've seen before. Sorry, you guys don't have this. You guys don't have this picture. You might have to just make a little note on the front side where it says friction. Okay. All right. So here is an example that most of you are probably pretty familiar with, right? Have you ever seen somebody rub their head with a balloon, right? You've probably done it before. As the balloon slides across your hair, if you have hair, there are different materials here, and those different materials have a different attraction for electrons. The balloon really actually wants to gain electrons more than the hair does. So these electrons that are part of the hair atoms get transferred over to the balloon. When that happens, what does the charge of the balloon become? Negative, because it gains electrons. But that means if the balloon becomes negatively charged, what has to happen? Hair becomes positively charged because of that whole conservation idea. And the hair and the balloon then stick to each other. Okay? Same thing happens if you run a comb through your hair. It's like, especially in the wintertime, if it's kind of like dry, running your comb through your hair, your comb will like stick to your hair a little bit, right? And or you might hear a little crackly noise, like there's little electric shocks because there are. Okay? But once we take this balloon away and the hairs are not attracted to the balloon anymore, what do they do to each other? Because if they have become positively charged from the comb or the balloon, what do positive charges do to each other? Repel. And this is what we call what? Well, I don't call it this, but other people might, right? No. What happens when your hair kind of like does this, right? Frizzy hair, right? That's frizzy hair, right? When you run that comb through your hair, run that brush through your hair, and the comb or the brush gains electrons, but the hair loses electrons. They are attracted to each other, but if we take the comb away, now all the hairs themselves are positively charged, and they don't want to, they move away from each other, right? And your hair kind of like wings it out and stuff like that, okay? I have this problem all the time.
All the time.
Totally. So, charging by friction. Friction requires movement. Okay? The second type of charging we talk about is charging by conduction, or conduction requires contact. Alright? So we charge by contact. There is direct contact between an object and another object, and electrons will flow from one to the other. Okay? That's just on the front page. So it's conduction down at the bottom. Okay. We haven't gotten to that one yet. So does it say conduction down at the bottom of your outline? So here, right? Down at the bottom, we talked about friction. Friction requires movement. We talked about conduction. Conduction requires contact. Okay? Yes, Laura? That's part of the book that we were gonna read. That was part of the book that we were supposed to read yesterday, but we were talking about other things for the beginning part of the period. We didn't get there. Yes? You remember that or no?
I remember in my notes.
Okay. There is one specific type of charging by conduction that we call grounding. Okay? In this case, electrons are transferred either to the Earth or from the Earth by contact. Alright? So, this is an example of, in the wintertime, if you drag your feet across the floor, right? and then you go and you touch somebody and you give them a little shock, or you go and touch like the light switch and it gives you like a little shock, okay? What's happening there is as we are going across the carpet, there is friction between your socks and the floor. And so we are causing a charging by friction between you and the floor. But let's say you have gained electrons. You have a negative charge. But do all those electrons like being near each other? Electrons all have what charge? Negative. They all have negative charge. So if we gain negative charges, that's great. We have a negative charge, but those electrons don't necessarily like that. If they can spread themselves back out or get to other positive charges, they will do so. And a lot of times we call that grounding. The Earth has a ton of atoms, and those atoms all have positive charges and negative charges. So, if we have a buildup of negative charge, electrons, they will look for a way to get to the ground by some contact. Alright? The light switch that you touch in your room or your living room or whatever is ultimately connected to the ground by all the wires that run through your house. Right? Or lightning. Right? Lightning, we build up a charge in the clouds. Do all those negative charges like being with each other? No, they look to try and get back to something where they can spread out, and that's the ground. But there has to be contact for that to happen. Right? Now you might say, well, wait a second, what about lightning? Lightning doesn't have contact. True. But there's air that goes between the cloud and the ground, which doesn't seem like a lot of contact, but it actually matters, right? Air is gas, and matter. Grounding requires contact between you and the earth. Alright? Some people in the other class brought up some things, like we talked about sometimes the kind of make an observation. You're not supposed to touch power lines, right? If they like fall down in the storm, yes, right? Stay away. But it's perfectly fine for a squirrel to walk along the power lines, or a bird to walk along the power lines, right?
Everyone is.
They have power. They wear boots.
We said, where do charges like to get to?
The ground.
The ground, right? It's okay for a squirrel or a bird to walk on the power lines, one, because they're insulated, they have a rubber coating on them. But two, if they're not touching the ground, the charges aren't real interested in going there, right? In theory, yes, right? But the more charges there are, the more that they will try and make their own way to the ground, right? Lightning makes its own path from the clouds to the ground because there's a ton of charges, okay? Does that make sense? You can prevent yourself, like in the wintertime, if you're wearing shoes, you don't get that shock from the light because you are insulated from the ground or you're not touching the ground. You have that sole of your shoe to protect you. That protects you from getting a shock from the light switch, but it doesn't protect you from sticking a fork into the socket. Right? You're talking about a lot more charges and a lot more energy, and they'll go right through your shoes because that's not enough. That's still, even though you're technically not touching the ground, that path is you only have to go through this much of your shoes. You know what I'm saying? But if you're on a ladder, right, like a plastic ladder, in theory you could touch that socket, or if you touch like a light bulb, you know, like you're changing a light bulb, you shouldn't like stick a fork into the light bulb socket, you know, right? In theory, you'd be protected because those charges can't get to the ground, but probably not a good idea to test that idea. So, because there's a lot of energy and they can get themselves to the ground if they need to. Okay. Yes, Ben?
I have a question.
Okay. I figured that's why you raised your hand. So.
Well,
Go ahead.
What if oxygen is actually poisonous, but it takes 80 years to kill us.
H2O2.
So.
What?
H2O2.
Okay, let's go back to tax
Poisonous.
observation.
That's 2 hydrogen. 2 hydrogen and 2 oxygen.
So, Pat, is that possible? I suppose it is.
It is.
Is it probable?
Gas.
Yeah.
Why? It takes us like 130 years to kill us.
Okay, it doesn't matter how many years it was.
They either die.
Yes, Shafar.
Did you find the
They
cure
die
for
from
cancer
some other cause,
like
or
we should have
oxygen.
Bill Gates right now?
Yeah, probably.
But they already
Superman, you got Europe getting
All right.
They just don't want to release it.
The third type of charging. Let's finish this up real quick, please. The third type of charging we call induction. Induction is a little weird because when you look at the objects that are charged by induction, if you count the actual positives and negatives, you'll see that there isn't actually a different number. There's the same number of positives and negatives. It's about how they are distributed. All right? So we will talk about this a little bit more tomorrow. And we'll also then get into electric force and electric field. All right?